So, hello NMR community and welcome back. It's nice seeing you again. Last time we have seen how rotations are fundamental for understanding solid-state NMR. We have learned rotations in Cartesian coordinates are rather cumbersome to treat, and we have learned that when we would write our Hamiltonians in spherical notation, the whole treatment simplifies greatly just because the rotation is then carried out in subblocks, and we are just rotating all the parts of our Hamiltonian that have the same rotation behavior. And this video is all going to be about spherical tensor notation, all the formalities about spherical tensor notation. So we will introduce them, we will say what they are, we will see what general spherical tensor notation for spatial and spin part of our Hamiltonian are. We will talk about the concept of the principal axis system, tensor parameters, these parametrizing our interactions, and this is still going to be a rather theoretical overview video, and in the next video we are really going to calculate through one specific example, in particular for the dipole coupling, such we can really then solidify the theoretical concepts that we learned in this video. And tensors always sounds like a scary word, and it always sounds like a scary mathematical concept, but let's start therefore from the beginning and let's look at Cartesian tensors. And Cartesian tensors are just objects, mathematical objects that are classified according to their rotation behavior. And we do this classification giving a certain rank for our tensor depending on how it rotates. And here on our slide we look at rank 0, rank 1 and rank 2 Cartesian tensors, and we see what different types of rotation behavior we are actually talking about. And when we start by rank 0 tensor, then actually this is nothing else than a number, a scalar, a constant. And how does a constant rotate? Well, it doesn't really depend on which frame you are in, it doesn't depend on which coordinates you use, it is not going to depend on where you rotate it. A constant is always going to be a constant, and that's why the rotation behavior of a constant is that it just stays equal to itself. And then we have rank 1 tensors, and rank 1 tensors are actually characterized by 3 numbers as, for example, a vector. And a vector, how does it rotate? Well, you just take your rotation matrix. We have learned this in the previous videos. You take the rotation matrix, you make the multiplication with your vector, and then you obtain the rotated vector. And finally, we have rank 2 tensors, and these are characterized by 5 numbers, and they rotate like symmetric traceless matrices. And how does the rotation work again? This time it gets a little bit more complicated because you take your rotation matrix and you multiply it once from the left and once from the right to your symmetric matrix in order to get the rotated matrix. And the key concept that we have for the Cartesian notation is that each 3 times 3 matrix A can be decomposed into a sum of rank 0, rank 1 and rank 2 tensors. And why do we say this? This is going to be also the case when we then look at our Hamiltonians in spherical tensor notation. It will also be possible to subdivide them into a sum of all our individual rank 0, 1, 2 tensors. And now let's move to spherical tensors, and we already said it in the last videos. Spherical tensors are a special symmetry adapted basis set, which is also subdivided and classified according to the tensor ranks, meaning according to the transformation behavior of all the basis elements. And when using a spherical tensor notation, then rotations are greatly simplified. Why? Because you're only rotating the individual tensors of the individual ranks, meaning that you rotate a rank 0 tensor, you rotate a rank 1 tensor, you rotate a rank 2 tensor, but you do not rotate the full object at once. And the rotations are carried out by so-called Wigner rotation matrices. And how does a spherical tensor look like? Well, you have a spherical tensor A, for example, A with a subscript L, and the L stands for the rank of the tensor, meaning that the L stands on how our tensor is going to transform when we rotate it. And a spherical tensor has 2L plus 1 components, and each component is then mathematically just denoted by an A subscript L subscript q. And let's look at an example. If we have a rank 2 spherical tensor, how many components does it have? Well, the rank is 2, so L equals 2, so meaning that 2L plus 1 equals 5 components. And so you can take your rank 2 tensor and you just write it as a vector of all its components. And what are the components? You just go through all possible values of Q, and all the possible values of Q go from minus L to L. In this case, we have A2 minus 2, A2 minus 1, A2 0, A2 plus 1, A2 plus 2, in total 5 components. And the main message is that as we saw for the Cartesian tensor and for general 3x3 matrices, when we said that we can expand any 3 times 3 matrix in a sum of tensors of different ranks, we can do exactly the same for every Hamiltonian, and we can write a Hamiltonian as a sum of spherical tensors of different rank L. And for most Hamiltonians that we are going to encounter in NMR, the maximum rank that we are going to have is rank 2, so we can have rank 0, rank 1, and rank 2 tensors that make up our Hamiltonians. And now what is going to happen? This is what we said already many times, and we repeated it also many times. As soon as we choose to use a spherical tensor notation for our Hamiltonians, and we decide to divide it up into a sum of tensors of different rank, the rotation of the whole Hamiltonian becomes very simple, because you only rotate each tensor component at once, separately, and this means that you will rotate the rank 0 components by a 1 times 1 block, you will rotate the rank 1 components by a 3 times 3 block, and you will rotate the rank 2 components by a 5 times 5 block, but you're carrying these out all individually, so the whole rotation matrix becomes block diagonal. You have this different block, and for each block, how the rotation looks like is actually described by this formula down here, where the D that depends on the Euler angles alpha, beta, gamma is called a Wigner rotation matrix for a tensor of rank L, and we're going to look at how these rotations are carried out in a lot of detail in the next video. But before we do this, let's now look on how to actually write a Hamiltonian in spherical tensor notation. And the general formula for every Hamiltonian in NMR, you can see it written up here. You start with your Hamiltonian and it's equal to a sum. And you do 3 different sums in this expression. The first sum that runs over I, this runs over all the interactions that you have in your system. So you will have a sum of, for example, the chemical shift anisotropy, you will have a sum with the dipole Hamiltonian, and so on and so forth. So for each of these Hamiltonians, you will subdivide it. So you will construct the general Hamiltonian from a sum of the individual Hamiltonians, and each individual Hamiltonians, you will separate it into the different tensors of the different ranks. So this is done by the second summation sign here that goes from L equals to 0 to 2, where you just divide each individual Hamiltonian into its different tensors. And we said it in NMR, we mostly encounter interactions that go up to rank 2, and this is why actually our sum over the L's goes up to rank 2. And then the last sum is actually a sum over all components of the tensors, of the subtensors. We said each tensor for rank L has 2L plus 1 components. How they are chosen, they go from minus L to L, and that's why our Q here goes from minus L to L. And we notice another thing when looking at this formula, when looking a bit more in detail, and it's hinted by the color coding that we use in the formula, that each Hamiltonian is made out of a multiplication between a spatial tensor AL and a spin tensor TL. And this is what we already said in the last video. Each Hamiltonian can be decomposed into a spatial part and a spin part, and both parts will be affected differently. If we have sample rotation, if we have RF irradiation, then RF irradiation will only act on the spin part, while sample rotation will only act on our spatial part. So it's very convenient to divide these two in the general formula for our Hamiltonians. Now comes a bit the overwhelming part of these formulas, actually the part on where we say, how do these spherical tensors actually look like? And you see the full list that is given here on the slide, both for the spatial part and for the spatial tensor as for the spin tensor. And actually, how these formulas are derived, that's a whole other topic. It's rather complicated. So this is a bit beyond what we want to do here in this lecture series. We want to just use the final expressions and then generate in the next videos our lab frame expressions for our Hamiltonians. So don't worry about where these expressions come from, but just remember that we have them tabulated and we can just plug them in as numbers. So actually now the last concept that we want to treat in this video, and this will conclude also our general overview about spherical tensors, is the concept of the principal axis system. And the principal axis system is a very special coordinate system in which the symmetric rank 2 part of our spatial tensor is diagonal, and it's fully described by 3 values axx, ayy, and azz. And when using this notation, when using the principal axis system, our second rank tensor is often described by 3 very important quantities that relate to this ixx, iyy, and izz elements that are actually the principal values. And these 3 parameters that we use for parametrizing our interactions in the principal axis system are the trace of our tensor, of our spatial tensor. So this is nothing else than the sum of all our diagonal elements, axx plus ayy plus azz, all divided by 3. Then we have the anisotropy of the tensor, which is just the difference between the azz and the trace. The anisotropy kind of gives us an idea on the breadth of the tensor, so on how big your interaction actually is. For example, if you think about a dipole coupling, the higher the delta, the larger your dipole coupling interaction and the broader your line is going to be in a static case. And then we have the symmetry of the tensor, and this is just given by ayy minus axx divided by anisotropy. And of course, the symmetry of our tensors gives us an indication a bit on where the center of gravity of our tensor is, which part of the spectrum that we're going to obtain will have more signal than another part. And with these parameters and the expression for the spatial tensor in the principal axis system, that, as we said, is just composed of 3 components, ax until azz, there actually we can also have expressions for the spatial tensor in the principal axis system that greatly simplify and that actually are only related to these 3 important parameters that we use for characterizing our interaction. And you see it, for example, the A00 component of our spatial tensor is just a trace times minus square root of 3. Then you have the rank the A2 plus minus 1 component of our spatial tensor that is actually always equal to 0 in the principal axis system. And then we have the A20 component that is related mostly to the anisotropy delta. And then we have the A2 plus minus 2 component that is related to the anisotropy and the symmetry. If, for example, we are talking about a symmetric tensor where the eta is equal to 0, then it would have no A2 plus minus 2 component, and we will see that this is actually the case for our dipolar coupling. And actually, for the moment, it looks a little bit like you have to believe me when I say that the dipolar coupling is a symmetric tensor with an eta equal to 0. Well, where does this information all come from? All of these parameters of this principal axis system parameters are actually tabulated for all the interactions that are relevant in NMR. You see the full table here on the right. And let's look, for example, at the row of with the dipole coupling. We see that the dipole coupling has no rank 0 component. It has no isotropic part. We see that the rank 1 part of the dipole coupling is also all 0. So the dipole coupling has, in fact, only a rank 2 component in its full expression. And the rank 2 component has an eta that is equal to 0, and it has a delta that is equal, that is our anisotropy of the dipole coupling, that is actually related to the 1 over r to the power of 3. So as we said, the smaller the r for the dipole coupling, the bigger the dipole coupling gets. And this is also now the explanation why it gets bigger, because the anisotropy of the tensor gets bigger, so the whole breadth of the tensor is getting bigger. And if we now look at another interaction, like for example the Zeeman Hamiltonian, there you see that we have only a rank 0 component and no higher rank tensors. And For the chemical shift Hamiltonian, it gets much more complicated. Why? Because you don't only have the rank 0 component, which is actually our isotropic chemical shift, the one where you see always our lines appearing, but we also have all a full breadth of other higher order interactions, rank 1 parts of the chemical shift anisotropy, rank 2 parts of the chemical shift anisotropy. All of these have a certain asymmetry and a certain delta, and this is actually what makes then our chemical shift actually becoming a rather broad tensor, and this is actually what is complicating a bit our treatment of the chemical shift anisotropy from a mathematical point of view, compared now to the treatment of the dipole coupling. So to wrap it up, what did we do in this video? We first defined a bit what spherical tensors is. We have discussed about what the ranks are, how they relate to the transformation behavior. We have seen how the treatment of the Hamiltonians in a spherical tensor notation greatly simplifies our rotation treatment, because our rotation matrix simplifies into a block diagonal matrix where each block is a Wigner rotation matrix related to a certain tensor rank. And then finally we have defined the principal axis system. We have shown what are the relevant parameters in the principal axis system. As a reminder, the trace, the anisotropy and the asymmetry of the tensor. We have seen that these values are tabulated for most interactions, so we can just use the tables in the literature. And then the most important thing that you keep in mind is that normally when we construct our laboratory frame expressions for our Hamiltonian, we actually start always from the spatial tensor in the principal axis system. We take the spatial tensor in the principal axis system and we rotate it by Euler angles into the laboratory frame. And all of this we are going to do in a great lot of detail in the next video. We are really getting hands-on and we're starting to write down the formulas, and we're starting to really make the rotation of the dipole coupling from the principal axis system to the laboratory frame. Then you will see how all of these concepts play in action in a real mathematical calculation, and this will then solidify a bit of all the abstract theoretical concepts that we have seen now by just talking about a real example. So as usual, thanks a lot for being with me. It has been a pleasure also this time, and I hope seeing you next time. The video link is down here this time, and until then, ciao!